All right, so we had looked through a bunch of examples yesterday, dealing with what? Or what kind of examples did we do yesterday? Or what was the big thing we did in almost every problem we did, if not every problem? Yep, z-scores was the big one. But today we're going to do the empirical rule, or the 68, 95, 99.7 rule for normal distributions. So, this first example of that stuff, Environmental Protection Agency fuel economy estimates for automobile models tested recently predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume that the normal model can be applied. And then A, draw a model for auto fuel economy, clearly label it, showing what the 68, 95, 99.7 rule predicts about miles per gallon. So we want to have our normal distribution here. I would recommend making it kind of big just so you can see everything you're writing in it. We want to start out with labeling stuff. So the mean is 24.8, and we want to go up from there with the 6.2 for the miles per gallon to give us our different standard deviations. So we have 31, 37.2, 43.4, and in the other direction we would have 18.6, 12.4, and 6.2. And this is highway mileage in miles per gallon, just so we have that label there. So from what we talked about the other day, where would the 68% be? What is it between? Yep, 18.6 and 31. Okay, because that is the stuff that's one standard deviation away. How about the 95%? Yep, 12.4 to 37.2. And the 99.7. 6.2 to 43.4. That's all we have to do for that. Okay, and we already basically answered B in the last part. So the interval that you would expect the central 68% of autos to be found, we said was 18.6 to 31.0 miles per gallon. What percent of autos should get more than 31 miles per gallon? Um, you're close. We need half of that. Yep. So it would be 100 minus 68 divided by 2. And the big thing we want to say is it's an approximation. So this is key. What percent of cars should get between 31 and 37.2? So what percentage goes out to 37.2? 95, so we start with that. What percentage goes out to 31? Okay, so we would subtract 68, and then again divide by 2 to give us an approximate of what? So half of that. 13.5%. Then for E, describe the gas mileage of the worst 2.5% of all cars. You're close in that. Basically, we're looking at the less than 12.4 because if we did this kind of as a reverse of this problem, 2.5% times 2 would give us 5%, and I want to know basically that bottom 5%. Then it's not exactly what it is happening, but that's more or less what's going on. So I can say then that that's 12.4 is, and I should say less than 12.4. And I guess we should still say approximately. What would you consider to be an unusually high miles per gallon and then unusually low? So I don't remember if we've talked about this, but a note that we should make if we haven't is that anything 2 standard deviations from the mean is considered unusual. So anything 2 standard deviations away or more in either direction is the case. So what would my unusually high be? That's 3 standard deviations away. 37.2 miles per gallon or more. And how about unusually low? Yep. Unusually low would be approximately 12.4 miles per gallon or less. Any questions about that one? Or any part of that? Alright, so on the next page there is several different letter parts to it. We're only going to do A through C right now, and we'll come back to D and E a little later. Okay, so on the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. When Tiger hits his driver, I'm assuming it's supposed to be hits with his driver, typo. The distance the ball travels follows a normal distribution with a mean of 304 yards and a standard deviation of 8 yards. What percent of Tiger's drives travel at least 290 yards? And then we'll draw a picture. Okay, so what does at least 290 tell us? Yep, so it would be 290 or more. Alright, so if I want to know the percent, what would I do to go about finding that? Yep. Z equals 290 minus 304 all over 8. And then what does that give me? Okay, so minus 1.75. But we want to know what that percent comes out to be. Hold on a second. I have to see. There's a way to do this. I'm just going to remember how to do it. Let me try this really quick on my calculator and make sure it's working, and then I might have to look that up in a minute and see. I need to see how to do this one thing because I'm blanking on what to do. It's not obvious. Okay, hold on. I think I figured it out. What? This is not working like it's supposed to. Okay, I might have to look at that later and figure out what's going on with the calculator, because right now it's not giving me the right answer. So, let's just set the other ones up, and then I'll look at that later, and we'll do that when I have more time to figure it out. So then the next one, what percent of Tiger's drives travel between 305 and 325 yards? How would I set that one up? Or what would I need to do here? .305. So we would do 305 minus 304. So we got to find the two different intervals. And then the other one would be the 325 minus 304 over 8. And what do those two give us? Yeah, 0.125. Yeah, I'm still trying to figure out why this isn't working like it's supposed to, so I'll have to look at that more later. And then, so we'll finish up with the percentage stuff later because we can't really do that right now. What distance would a ball have to travel to be at the 80th percentile of Tiger's drive length? Draw a picture. Hold on, we might not be able to do this one either unless this is working. Yeah, this currently isn't working, so just skip that one for right now. Let's see if we can do something on a different page. No, I'm just going to have to stop and look at this. Yeah, we should be able to do this up on the next page. So let's go to that, and we'll come back to that later once I look and figure out what's going on with this. Alright, so this next thing, when are normal models appropriate? In regards to like a histogram. It's not really what I'm looking for. What about the shape and spread of the distribution? Unimodal, what else? Nope. What's the other option? Symmetric. Okay, because we want our normal model to be like the thing that looks like a hill. Okay, so we want it to be unimodal and symmetric. And then also something we didn't talk about is, or I don't think we did, when the normal probability plot is a straight line. Okay, if it's not symmetric, okay, the plot's not going to be linear, we can't use the normal model. Okay, so if the histogram is unimodal but not symmetric, the normal probability plot is not linear, and thus we can't use the normal model. Okay, but if these top three things are true, then we can use the normal model. Alright, so then this next problem is about the shark. So whenever you're done writing that, start typing in all these numbers because there's a lot of them. Make sure you have 44 numbers in your calculator when you're done. Just in a list. Once you have all those in, go and make the histogram and then copy the picture of it over. Well, you need to use a stat plot to do it, so you'd have to have it on. Just make sure there's nothing in your y equals. Second stat plot. And then just set it up for a histogram and then hit, once you have everything typed in, hit zoom 9. No, second stat plot. This button up here. Yeah. No. You don't need to trace it. Zoom 9 and then and it'll graph it. What do we notice about the shape of this distribution? Yeah, but what do we know about the shape and spread? No, I would say that it is roughly symmetric. Because everything's still like pretty condensed right here. Because honestly, this over here, probably an outlier. Honestly, so we kind of can ignore that. And it's unimodal. Yes, this one is a little bit shorter, but it would have to be like several of them between to consider it bimodal. Alright, so then on to the next page, this problem continues. So you might want to still keep the numbers and stuff handy. But it wants us to calculate the one variable stats. So do you guys remember how to do that? Alright, so do that and list off all of the X bar, your standard deviation, and then your 5-number summary. And your IQR. Also check the fences. Q1 minus 1.5 IQR and Q3 plus 1.5 IQR, just to see if we have any values that are outliers. Based on that, do we have any numbers that are outliers? What number is an outlier, if so? Changing your mind? No. Do all the numbers fall within that range? Yep. So we don't have any outliers. Okay, so from the histogram, it kind of looks like maybe there's a possibility of one, but we see now that there is not. Alright, so then the next part, calculate the percent of observations that fall within 1, 2, and 3 standard deviations of the mean. How well do these results compare with the 68, 95, 99.7 rule? Alright, so we need to first draw the picture here. Sorry, I was checking to make sure something on the calculator was working since the other thing wasn't working. Trying to make sure this one does work, and it does. So, drawing a rough sketch of what we have going on here. Okay, our mean was 15.65. Okay, and then our standard deviation was 2.56, so we need to add 2.56. $18.21. Add it again. 20.77. And one more time. 23.33. Okay, and then we need to do the same thing the opposite direction. Subtracting. $13.09. 10.53. 7.97. Alright, so now I want to know what percent fall within 1, 2, and 3 standard deviations of the mean. And so basically I need to set up 3 things here. 1 standard deviation, 2 standard deviations, 3 standard deviations. Okay, I know that the amount is going to be out of 44 because that's how many total numbers I had. Alright, so on your calculator, you're going to hit the button that says Stat. Then you're going to hit the button that says Sort A. And then you're going to plug in L1 to that by hitting Second Stat, and that's going to bring up the list options. Okay, and that's going to make your list put everything in numerical order from smallest to largest is what that's going to do. Okay, the A is for ascending, so it's getting bigger. If there's another one that says sort D, that means descending. Okay, so when you do that, then we can count up and see what things are those distances away. Okay, so I want to see how many numbers fall in the 13.09 to 18.2 range. So I'm just going to literally go down and count them up. How many did y'all get in that range? So you'll have to go back to, after you sort the list, you'll have to go back to edit, and then you'll have to count up all the ones between 13.09 and 18.2. Yeah, stat edit, and then just look through and then just arrow down and count up how many are in that 13.09 to 18.21 range. How many? 23? $13.09 to 18.2. 18.2. 1 standard deviation away from the mean in both directions. I got 33. Wait. Now I need to recount them because that's not what's on this paper over here. 18.2. Sarah, how many did you count? You have 31? Do you also have 31? Okay, well maybe I just miscounted. Alright, so 31 out of 44. 2 standard deviations away, it's going to be 31 plus the numbers that were from 10.5 to 20.7. So if there's any that were outside of that. Yep. So then this one is 42, and then we know that everything else has to be included in the last one because we didn't have anything outside of the 3 standard deviations. So that one's just going to be 44. Okay, so 44 out of 44 is going to be 100%. What's 42 out of 44? And then what's 31 out of 44 also? And 31 out of 44. Okay. So based on that, how similar is this to the rule, or how does the results compare to the rule that we have, the 68, 95, 99.7 rule? Yeah. So I would say that it's very similar to the rule. So the rule and then this problem individually makes sense. There's only like 3 more minutes, so we're going to stop there. I know we still have a little bit left with this, so make sure you keep all those numbers in that stat plot. If you need a plot for something else, use something other than the L1 that you just put that in, because we need to graph this stuff tomorrow. So